Alright, so in this video I'm going to talk about moments and also link them to the centre of mass. So first of all, what is a moment? So essentially it's the turning of effect of a force about a pivot. And you can calculate it by multiplying the force by the perpendicular distance here. So if we draw a beam and we have its pivot at this end here, and we apply a force normal to the beam, essentially this is going to be the perpendicular distance and this is the magnitude of the force. Now a special case of this is something called a couple. So this is when you have the pivot at the centre of the object here and you have equal and opposite forces acting on it. So these forces are both acting to rotate it clockwise and the forces are equal in magnitude but in opposite directions. So that's known as a couple. So let's have a look at some more examples of perpendicular distance, some slightly more complex ones. So if we're taking moments about this end, which means we're putting the pivot at these ends of the objects here, essentially in terms of establishing what the perpendicular distance of the forces are, so this one, if we drop a dotted line back down so we're level with the pivot, the perpendicular distance is this length here. So it's a distance. So this is the direction of the force, this is the direction perpendicular to force. So it's this distance here. Likewise for this one, draw a dotted line, it's this distance here. This object would be trying to rotate the object round this way. This force would be trying to rotate the object round that way. So they have opposite directions. So this one would be positive because it's clockwise, this one would be negative because it's anti-clockwise. For this one here, so in the direction that's perpendicular to this force is in this direction here. So it's this distance that's important this time. So between essentially level with where your pivot is, this distance here, and this one, same as before, it's this distance in there. So those are some slightly more complex versions of perpendicular distance. It's just the distance that is perpendicular to the force. Alright, so let's move on from that and look at some examples of putting moments in practice. Okay, so we've got a 2 kg block. It's placed 20 centimeters from the left, and that's measured to the center, by the way. And the table is length 1.0 meters. There's a weight force from the table of 20 newtons. So let's label that on here. So that's the weight force, and it's going to act from the center of the table. And it's supported at both ends by F1 and F2. So the first thing we do is calculate the weight force of the block, so W1. And that's going to be the mass times by G, which is going to be 2.0 times 9.81, which is the value of G we use in the physics course. And if we type that into our calculators, we end up with a value of 19.62 newtons. I'm not going to round that at this stage because we're going to need it in the calculation. So we've calculated W1. So this is where we're going to use the principle of moments. So if this whole system is in equilibrium, we can essentially say the moments going clockwise are equal to the moments going anti-clockwise. So what we're going to do is we're going to take moments about a pivot point that we're going to place here. I could have placed it anywhere, but seeing as we don't know F1, I'm going to put it there. Equally, putting it on F2 would be extremely a valuable thing to be doing. Okay, so if we look at the moments going clockwise, so the force is trying to make it go clockwise, so you'd have W1 times the distance from the pivot of that one, and then you'd also have the W2 times the distance from the pivot. So that's going to be this 19.62 times by 0.2, because that's the distance of that from the pivot, and then 20 times by 0.5, because the mass of an object, or the weight force of an object, acts from its geometrical centre. So if that's 1, that's going to be 0.5, and if we calculate that, we'll end up with the value. Let's just type that in. 62 times 0.2 plus 20 times 0.5. So we end up with 13.9 2, 4, blah, 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 blah. In terms of them going anti-clockwise, we'd have F1 D1 plus F2 D2, which equals F1 times 0, because the force is applied at the pivot, so it has no moment, plus 1.0 times F2, so that's just F2. Essentially, we can establish then that if it's an equilibrium, the sum of the moments would be equal to 0, which means that essentially clockwise is equal to anti-clockwise. So we get F2 is going to be 14 newtons, giving it to 2 significant figures. And if it's in equilibrium, we also know that F1 plus F2, which are the two forces acting up, must be equal to W1 plus W2. So we can, if we want to solve for F1, it's going to be W1 plus W2 minus F2. So that's going to be 19.62 plus 20 minus 13.9, which gives us a value of type that in 26 newtons, giving it to 2 significant figures. So in this section here, we've used that the resultant moment is 0. This section here, we've just used that the resultant vertical force is 0 to solve that question. Alright, so let's have a look at a different example. So we've got a 1 meter rod hinged at one end. So let's show that on the diagram. Essentially, we've got a hinge at this point here. And it's supported by a force F1 at the other end, so that's what we can see here. And it wants us to calculate the maximum support force if a load of 200 newtons is applied. So, if this is the hinge, we're going to take moments about the hinge. Since we don't know any of the forces at the hinge, it makes sense to take moments about there, so we can multiply them by 0 in all our calculations. In terms of maximising F1, if we remember that the moment is the force times the distance, so we want to place the 200 as far as possible from the pivot to maximise F1, so that's why we've placed it there. So if we look at them going clockwise, it would just be 200 times 1.0, so 200 Newton meters. Going anti-clockwise, it's F1 times 1.0, which is F1. So if they're in equilibrium and the sum of the moments equals 0, that means that F1 is 200 newtons at that particular length. And if we then resolve vertically, so F2 plus 200 minus 200 would be equal to 0 if it's an equilibrium, so then therefore F2 equals 0 newtons. So in fact hinge is actually supplying no force at that given position of 200. Incidentally, when you look at some other questions later on, if we, apply a force like this, there will also be a force, actually I've gone in the wrong direction, actually like this from the hinge. So forces from the hinge can be perpendicular like this, so you can get horizontal and vertical ones to compensate for this. But in this example, because we only had vertical forces, the force at the hinge would also be in a vertical direction. So for part 2, we're going to move the 200 Newton force to the middle of the beam. And remember, we still got a hinge here. So let's take moments about the hinge and get rid of one of our variables. So going clockwise, it would be 200 times 0.5 this time. So it would just be 100 Newton meters. and then going anti-clockwise, it would be F2 times 0 plus F1 times 1.0, which is F1, which essentially means that F1 is equal to 100 newtons. If we resolve in the vertical direction, we know that F1 plus F2 is going to equal 200 to be in equilibrium, so that gives us F2 of 100 newtons as well. So when we apply the load to the middle of the beam, essentially the forces being shared between the two supporting locations like this. So what if we introduce some angles? So a rod is placed with one end on the ground and forces of 10 newtons and 5 newtons are applied in various locations on the beam. And we want to calculate the angle of the slope if the object is in equilibrium. So since things we've forgotten, the force on the ground is going to have to be in two directions because we've got a force horizontally, so there's going to have to be a horizontal reaction force, and there's going to be a downward force, so there's going to have to be an upward one here to keep it in equilibrium. And let's call this location where it touches the ground A. So we're going to take moments about A, so anything at A is multiplied by 0. And I'm going to say the beam is length L and at an angle of theta. So essentially this distance here is going to be L. So we need some perpendicular distances. So the 10 force, we need this distance here because that's the distance perpendicular. So that would be L sine theta. So essentially what we have going clockwise, we have 10 newtons times by the length sine theta. And then anti-clockwise, we've got 5 newtons, and we've got half the length here, and we need to multiply it by cosine theta to get this length here. So because it's halfway along, it's going to be L over 2, and this time it's going to be cosine of theta because we want this side here. And remember, the sum of the moments should be 0. So essentially 10 L sine theta should be equal to 5 L over 2 cosine of theta. So you can see at this point the length of the slope is immaterial. Let's clean up these fractions by multiplying both sides by 2 and dividing by 5. So you multiply by 2, you get 20, divide by 5, you get 4 sine theta over cosine theta is equal to 1, which implies that tan theta is equal to a quarter, which implies your theta is going to have the value, let's take inverse tan of 0.25, an angle of 14 degrees, essentially. So using this identity, sine theta over cos theta equals tan theta is going to come up sometimes in these questions, so it's important that you know that. And then it wants to calculate the magnitude and direction of the reaction force on the ground if the rod makes the angle calculated. So if we think, let's call this the reaction force vertically and the reaction force horizontally. The vertical reaction force must be equal to 5 newtons because essentially it needs to counteract this force here, and the horizontal force must be 10 newtons to counteract this one, so it's going to be in the opposite direction, so it's actually minus 10. So R is going to be the square root of minus 10 all squared plus 5 squared, which is a root 125, which is going to come out at 11 newtons. And then the angle of the reaction force, let's sketch a diagram so we can see what angle we're talking about. So we're going to end up with a resultant force in that direction, where you've got these two components here. So I'm going to give the angle to the horizontal direction. So we know that this side is going to be 10, this side is going to be 5, so theta is going to be inverse tan of opposite, so 5 over 10, so inverse tan over half, half, which is 27 degrees. Okay, so that's how you can essentially use moments to solve angled equilibrium problems. So let's move on to look at the centre of mass and some toppling. Okay, so an object topples if its centre of mass goes outside the base. So if we have an object that's on a slope, and it's an object like this, and its weight force acts from its geometrical centre. So if we draw the weight force in there, we can see that the limits of the base are here and here. So what you can see is that this is actually going through inside the base, so this one is not going to topple because the weight force is inside the base. Let's make it a bit steeper, where you have it like that. Here's your geometrical centre, like around here. Draw the weight force down, and we can see here that the weight force has now gone outside the base here. So what you can see is going straight through there. So this is going to topple over. So this is the reason that to make objects more stable, you increase the size of their base, and you try to bring their centre of mass down towards the ground. So the lower you can get the centre of mass, the better, because the harder it is to topple. So let's put this into practice. So essentially, an object's going to topple if there's a moment acting to rotate the object outside of the centre of base. So this one is going to act to rotate the object in this direction, whereas this moment force is going to prevent it from toppling over. So let's have a look over here. So if we look at this diagram here, if we apply a force in that direction, what's going to happen is the box is going to rotate. So it essentially gets tilted in this direction. So it's going to rotate about the point A. And you can try this for yourself if you put an object on a table and push it. If you can get it to not slide, you'll see it will rotate about the side opposite to where you're pushing. So let's take moments about A. So the perpendicular distance for the force going in the clockwise direction is the height of the box, which is 20 centimeters or 0.2 F. Going anti-clockwise, we've got the weight force, because essentially this is trying to go around this way. And so what we'll have is the weight force, so 5 times 9.81, and then it's going to be half the size of the base, so 0.04 divided by 2, and so we can calculate that straight away. So 5 times 9.81 times 0.04 divided by 2 gives you a moment of 0.981 Newton meters. Sum of the moments is equal to 0 when it's on the point of tipping, so essentially if any force greater than the one calculated, it will tip. So we get a value of force is going to be 0.981 divided by the perpendicular distance of it, and when we adjust our answer divided by 2, we end up with 4.9 newtons here. So essentially, any force greater than this is going to mean the moment is going to act to rotate it, and then what's going to happen is it's going to topple over. So this is like the minimum force that would cause toppling to occur. Okay, so a couple of recap points. With the centre of mass, the weight force acts from the geometrical centre of the object. So if you want to find a geometrical centre, You can have two lines of symmetry and you find where they intersect is a very easy way of doing it. So unless you're told otherwise, centre of mass is geometrical centre. Occasionally they tell you where it is instead in your calculations. And in terms of stability, the lower your centre of mass is, the better, and the wider your base is, the better also. And those are the key things you'd need to know about the centre of mass and stability.